One thought is, so when we got up here into 5.4, we started doing what we call these definite integrals. An integral from 2 to 4 of 1 over x dx. I don't know, it's a definite integral. And when we do the definite integral, we decided, well, anyway, can you guys do this one? This one, I don't know if you know this one. You got to know is antiderivative.
Natural log.
Good. And it's not a power rule. A lot of these are power rules. You move it up and do a power rule, but not him. He's not a power rule. He's the natural log of x, right? If we kind of remember our derivatives, he's the natural log of x. And remember, so we said we don't need a plus c. It does have absolute value on it, although when I evaluate this from 2 to 4, that absolute value is about to become obsolete or irrelevant because you're plugging in a 4 and you're plugging in a 2 and it doesn't matter. Well, anyway, so that's how you finish this. It's the natural log of 4 minus the natural log of 2. And, it's some decimal. Your book will get fancy here. You plug in the 4, you plug in the 2, you subtract. Your book will get fancy, and it's not fancy. It's just using a little log properties here. Maybe you remember that the subtraction of 2 logs is actually, I could write it as 4 over 2. Now that's just a log property. That's not necessarily calculus there. And then that's the log of 2. So, it's possible you could do this problem and look up the answer and think, what the hell happened? Well, whenever there's logs involved, your book might use some log properties. And your answer might look different than you thought until you realize how to use those log properties. So I don't know, that's one idea. There's nothing difficult about this here. What did I want to say? Oh, I wanted to say so when it's a definite integral, we don't put the plus c, right? I want to just show you that if you did put the plus c, what would happen? What would happen is, so you'd have a plus c here, right? And then you'd plug in the 4 and you would get, watch this a second, I'll just show you that. And you'd get the log of 4 plus c minus, then you'd plug in the 2 and you'd have the log of 2 plus c. Now guess what's going to happen to those c's? If you distribute the negative sign, they're gone. And they'll always be gone, not just for this specific example, but for any. That's why we don't put the plus c's. I mean, you're going to have a plus c here, you're going to have a plus c here, you're going to subtract them, and whatever that plus c is, it goes away. So maybe that helps you realize you don't need the plus c, or bring a little consistency to your thoughts. So we just don't write it. So cool. The other thing, quick, is if I wanted to show you what this means or what this represents, I guess the only, we'll learn, especially when we get to Cal 2, we'll learn other uses of integration. And an integral can mean a lot of things, actually. But as of now, we kind of interpret it as area under a curve. And so if I wanted to interpret the meaning of this, I could interpret it as the area under this curve. This curve is shaped like this. Y equals 1 over x. I mean, I could use my graphing calculator to help me, but I kind of know what stuff looks like. So it's this curve, and I guess I'm integrating from 2 to 4. Let's see, that's 1, 1, 1, 1's a point. So 2 and 4 might be way down here. So I'm integrating from, I found this area, I guess, you guys. Under the curve, down to the x-axis, that's that area, that number, whatever that number is. Okay, whatever. I don't know. We probably should do some more definite integrals. This is just an example of 5.4. I'm just talking because you're not. Again, you got questions or thoughts or concerns, you can interrupt me, get my attention and do something. But otherwise, I'm going to keep talking. One thing, here's something in 5.4 I never got to. It's called the mean value theorem. We did a mean value theorem for derivatives. I never tested you on it, but we talked about it. This is different. This is a mean value theorem for integrals. It says this, it says if f is continuous, what does it say? F is continuous on an interval from a to b, then there exists a number c in the closed interval a to b such that this happens. So really, let me just get to the point. It's, if I'm doing an integral from a to b of f of x dx, you know, kind of like I just did, what they say is there's this number c such that f of c, such that this integral equals f of c times b minus a. Now, you know, this is a math professor writing math on the board, and it's tough for students to interpret, so I help you interpret it. You know, what's going on here? Well, just abstractly, you got some function f of x. You are integrating from a to b. And one interpretation of what this is here, over on the left-hand side here, is that it's the area under the curve from a to b. So here's a, you know, this is what this is. Look what they're saying it is. They're saying it is for some c in the interval a to b, you can plug that c into the function and get a height. Watch this. You plug that c into the function, which gives you a y value, which gives you a height. And then you can take that height, if you don't mind, it's a y value or a height there. And you can take that height and multiply it by this b minus a, which is this distance b minus this distance a. This b minus a is this entire width, is what that is. So what they're saying is, what are they saying? The area under the curve could be some height times some width. This width times some height. What they're saying is that there is a sort of a mean value here, or what the book later calls an average value, or kind of an average height. I would kind of call it a height, where, what am I saying? That the area under the curve, it's hard to say. You guys should try this job sometime. I'd rather be digging ditches than this is hard. All right. The area under the curve is represented by the integral. Another way to represent that area is with a rectangle that has this width and some height. They're claiming that there exists a height somewhere in here where if you just topped it off at that height, you would have the area under the curve. So every integral can be interpreted as the area under a curve. Here, let me just try this again. Just a little more abstractly. If I had some function, there's some area under this curve. The mean value theorem says that there's some value c somewhere in here that if you can go up and find the correct height there and top it off with that height, that that width times that height is the equivalent area as the area under the curve. Takes me a while, but maybe I eventually said what I wanted to say. That's what this says, that there is a height times a width. I mean, I can represent any crazy curvy area. If I can find the right place, I can have a height times a width that's equivalent to that area. And then we eventually refer to this number here as the average value. In fact, so this is the mean value theorem, and then your book says the average value of a function. They use this term, they call it the average value of a function, and they say it's this. Watch this. 1 over b minus a times the integral from a to b of f of x dx. Now, can you tell what they just did? What did they just do? How did they get from here to here? This is the mean value theorem. I tried to explain it to you. And then from here, they got to this. I think they
Reciprocal of B minus A?
I think they divided by B minus A. I think they divided by B minus A. And, you know, and instead of writing as divided by B minus A, they got it out front. It's 1 over B minus A. You see it? That's what they did. And so if they divided by B minus A, then what they got is this F of C, which I'm describing as some average height, some height that balances out the area. Cool. You know, it's this height that balances out the area, like I'm sort of describing. It's this average height. You know, to tell you the truth, what it is, I mean, here's another way to describe it. Between A and B, there's a height. At that X value, there's a height. At that X value, there's a height. At that X value, there's a height. 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 They're all Y values. Y value, Y value, Y value, Y value. Thousands of Y values in there, right? Actually, infinite number of Y values, actually, if you divide it up enough, right? Mm-hmm. Average them all, please, and there's the average Y value. Right there. Do this formula, you get the average height. It's the average of all those damn Y values. It's the right from in that interval on this function. So those are cool ideas. You know, I don't really make you memorize these formulas. When I put a question like this on a test, I kind of say, "Oh, recall the mean value theorem," and I write it down for you on the question. And then how do you use it? You know, I kind of did that to you on your last test with your dy and delta y. I gave you the formulas and told you and said, "Here, you know, try this," and it didn't go too well. But anyway, you should practice a few of these problems. Maybe I think there's some in the homework in 5-4. Maybe I could practice one now. Let's see if I could practice one with you. If I look at 5-4 homework, using the mean value theorem, there's one, 49 through 54, and then finding the average value. That's kind of more what I'm interested in. I only assigned a couple. You could try a couple more than I assigned. I could try this 56. Let me try this 56. It looks kind of tricky. I'm in 5-4, and I want to try this number 56, which says find the average value. They give me a function, and they give me an interval. The function is kind of wild. 4x squared plus 1 over x squared. 4x squared plus 1 over x squared. And they give me an interval of probably, 1 to 3. I'm working on 1 to 3. You know, it'd be cool to kind of, again, pick up my graphing calculator, maybe sketch this and show you this. I'm not sure what this looks like exactly, so I'd have to work on that a little bit. I don't need a picture to show you this, though. The question wants the average value. That's what they want. And if I give you the formula, or look over here, here's the formula, maybe I could do this. I mean, the average value is just a formula, but it is kind of nice to see what it is. It's some average height of this function. This function, between 1 and 3, it's doing some crazy stuff, but I'm looking for the average height between 1 and 3. If I try this formula, let's try it. It's going to be 1 over b minus a, which is 1 over 3 minus 1, of course. By the way, that's kind of that width, 1 over the width. And then multiply by this area from 1 to 3, this integral from 1 to 3 of that function. So now I got to integrate this function with respect to x. So that's it. I'm integrating this function with 1/2 in front of it, right, you guys? I mean, you know, again, sometimes formulas just turn out to be formulas. There are lofty ideas behind these formulas. But you guys okay? Find the average value. There's the formula. Here we go. So this is a 1/2, and it's in front of this integral. Constant can sit in front of this integral. And I got to try to integrate this from 1 to 3. I'm a little confused how to integrate this. I think I got to do a little bit of algebra here first. Any suggestions?
Don't you plug it in?
Well, I want to integrate this. I need to integrate. Oh, whoa. You have to integrate before you evaluate. Yeah. So I have to integrate this function And I'm saying I don't know, it's antiderivative. It's not coming to me. I mean, I can't see it, nobody does. We need to do a little algebra first.
Should you distribute?
Distribute the 4?
Yeah.
All right, that's one thought. I still don't get any much past that though.
Move the
Then
x
what?
squared up and then multiplied it.
Split it up. Yeah, split it up. Right. When you got several numerators over one denominator, you put every numerator over that denominator, you get a bunch of separate terms. You're allowed to integrate separate terms. Right. That's what we should do. By the way, you guys said distribute the 4. You know, I'd rather pull the 4 out. There's this concept of pulling constants. Multiplied constants can get pulled out in front of the integral. So I'll just pull the 4 out. Now it's multiplied by this half. And then you're saying I got x squared over x squared. What's x squared over x squared?
1.
A 1. And then I have a 1 over x squared, which I could call 1 over x squared, but really I'd like to call it
X negative 2.
Good job. So I just did a couple moves there. You handle that? I pulled the 4 out, and I busted up the numerator.
And then you multiply 4 times that?
Sure.
Okay. Which is 2.
Which is a 2. And you know what else I'm going to do? I'm going to integrate. Here we go. Can you guys integrate a 1? Very good. And can you integrate an x to the negative 2? Good.
Negative 1 over
X to the negative 1, divide by
negative 1.
negative 1. That's how you integrate. It's easy.
Which is negative 1.
So we just integrated. We got a 2 out front, and I need to evaluate from 1 to 3. That's what you do with definite integrals. You evaluate from 1 to 3. Maybe that x to the negative 1 is bothering you a little. It bothers me a little. Let me just change something here.
1 over negative 1 over X.
I'm just gonna, before I evaluate, I'm gonna just change it. What is it? Oh yeah, put them back in the denominator. There's an x in the denominator, and put the negative sign. I put the negative sign in the numerator. Is how I do it.
Right.
So I'm making it a negative 1 over x is what I think it is. Don't you?
Right.
Cool.
From 1 to 3.
All right, now I'll put in my 1 and my 3. Here I go. I plug in my 3. It's 2 times 3 minus a third. That's what happens when you plug in a 3. Minus the 2 times, and then you're plugging in the 1. 1 minus 1. That's kind of cool. You guys doing all right? Integration's fun. I mean, you got to get the concept of working on how to do the antiderivative, and then after the antiderivative's over, you have to plug these numbers in and evaluate. I mean, it's an easy place to make mistakes. I mean, but it's no longer calculus, you know, plugging numbers in, and it's just kind of algebra, but be careful, please. Anyway, that's a big 0, and this is 8 thirds times 2. I think the answer is 16 thirds. Again, you know, for the purpose of understanding what the hell we just did, maybe I might like some kind of an illustration of this. I am working on this function from 1 to 3. Can anybody help me graph this function? How do you, I don't know, can you go to your graphing calculator and graph it? Can you help me? I don't know what I'm trying to think. It's probably just something like this, I guess. Maybe I'm wrong. Huh. So you type this in, you put parentheses on it, you divide it by x squared, and you type this in and you took a look at it, and what are you saying? Yeah, I got you. You know, it's undefined at 0. I see what she's, okay, so over here, she said it goes up like this.
Right.
Yeah, but it's not connected because it is undefined at 0. There must be. So anyway, so in a way I'm not wrong. I was over here looking at 1 to 3. She was kind of looking at the whole thing. And I'm looking over here at 1 to 3, so I think I'm right. Don't you think I'm right? Mm-hmm. Okay, cool. And what did we find? I don't know, whatever this, I don't know what this height is. I don't know what this height is. But what we found was the average height The average height is 16/3. 5 1/3. I mean, that's
Right.
somewhere in here. We found this average height, 5 1/3. Average value of the function is what it's called. The average value of the function. It's a y value. It's a function value. It's known as f of c. You guys all right? All right, I'll quit. What I didn't find was the c value. They didn't ask for that in this problem, but sometimes they want to know that c value guaranteed by the theorem.
Yeah.
What I found was the f of c. I found the height,
Right.
and I don't really care about finding that c value, but there is some c value that gave me that height, which is an x value. I'm good. I'm happy. The other funny thing in 5.4 that I never got to, I'm cleaning up some stuff I never got to. The other thing in 5.4 that I never got to was what they call this, well, hang on. They've got this, they can, they do this, bless you, they integrate a function, f of t dt, and normally when you integrate a function and you put bounds on it, your bounds are numbers. You're integrating from 1 to 3 like we just did, or 2 to 4, or 0 to 8, or anyway, this is funny. They're doing this thing from 0 to x. So they leave this upper bound kind of as a variable. Anyway, and then they change the variable in here because you can't have that variable match this variable. It gets a little confusing. And then so they call this a function. They call it big capital F of x. And you could kind of call it, listen now, you could sort of call this an accumulation function. I like this actually. Because and let me explain something to you. So here we go. Let's integrate this. Now it's abstract. It's f of t. So how do you integrate an f of t? We don't know. But the answer will be some capital F of t. Do you agree with that? It'd be the antiderivative of little f. We call it capital F. So it's f of t. I mean, it would be in t's. But then I would evaluate it from 0 to x, wouldn't I?
Right.
So then I'd plug in an x, and then I'd plug in a 0 and subtract it.
So it's just F of x,
So I just get f of x.
which is,
I could say it's minus f of 0. I don't guarantee that that's a 0, although they kind of do here. Huh. That bothers me a little, but not too much. Are you guys with me? You integrate with respect to t, and then you would plug in the x. So you get some function of x. And what it's kind of like is, again, this is the area under a curve. This is my function. It's the area under the curve, this time from 0 to where? From 0 to x. See, so it's kind of like this upper bound can be a variable. Right now, I mean, here it is, and so it would be this area. But if x moved slightly, it would be over here, and you'd get more area. And if you changed x and let x get bigger, you would be sort of accumulating the area under this curve. And so you can sort of call this an accumulation function. It's accumulating area under the curve. I don't know if I want to really do a problem. I wanted you to see that idea. I might do a problem. But then here's another idea. This is called the second fundamental theorem of calculus. It's kind of funny. Watch what it does. Watch what it says. It says if you have one of these if you have one of these integrals with this variable bound, and you took its derivative, guess what you get? It's kind of weird. I mean, it's kind of weird. But look, you're integrating some function, and then you're taking the derivative of it. And you know how integrals and derivatives work. They kind of cancel each other out. I mean, so if I integrate this, I'll get some, you know, like I did over here. If I integrate this, I get some capital F. I plug in the x, I get some capital F of x. But what if now what am I supposed to do? Take his derivative. And if I take the derivative of capital F, I think I get back to little f. So this is just f of x. In other words, if you ever see this, the derivative and the integral sort of cancel each other out. You get what's inside, is what this is saying. Kind of obvious. And I don't know how useful it is. I don't use this theorem too much. I'm mentioning it. There's a homework problem or two. That's all. I don't like it as much as this average value. I like that a little better. So what am I doing? I'm hitting some topics here that I skipped, but I kind of, as you can tell, they're not my favorite topics anyway. Well, so let's do my favorite topic. You ready? My favorite topic is 5-5. I love to do I need to do these. When I talk about 5-5, I call it U-substitution. U-substitution. Your book calls that a change of variable. They also call it, the title is Integration by Substitution, so I'm with them. They call it changing variables. You change from whatever variable it is to U. We tend to use the letter U. And sometimes I don't think students understand the need for it. Listen, so you need it for a problem like this. You need U-substitution. Now this is one of the easiest integrals ever. We haven't done too many of them. It's one of the easiest integrals ever because you remember the original? I mean, we learned how to integrate an e to the x. How do you integrate e to the x? It's e to the x. We know that because we know his derivative was so easy, right? What's the derivative of e to the x? E to the x. So what's the integral of e to the x? E to the x. Right. So it's cool. It's easy. All right, well, guess what? So is this. This is really easy. But the answer is not e to the 2x. Because there's a little 2x there, you might be thinking about a chain rule, but we're not doing a derivative. Derivatives have chain rules. We're doing an antiderivative, so maybe we're sort of doing a chain rule backwards. I'd rather you not think of it like that, though. I'd rather you think of it as, this is the rule, and in order to fit this rule, this has got to be a single variable x. Or in other words, we use u, and so if I can get it in, if I can make it an e to the u du, then I know the answer is e to the u. So I need it to look like this so I can shout out the rule. And right now it sort of doesn't look like that. It's more, if it's ever more complicated than just a single little x, a 2x, a 4x, then it's a u. Now let's go through the steps. So the steps are, I got to call this a u. Listen, I'm sorry, this gets, again, it's hard to explain this stuff. What I'm suggesting is that the wrong answer is, oh, you're integrating an e function, it's just himself. You're done. And this is wrong. And I need to explain the steps involved to show you why it's wrong. But it has to do with that backwards chain rule kind of thing, but I need this U substitution to fix this. So watch what I do. Wait. Why is this wrong? Here you go. Hang on. Okay, so maybe we think this is the damn answer. All right, hold on, it's wrong. All right, and one way to check it is do his derivative.
Right.
What's his derivative? Now I'm doing a derivative. I'm sorry, by the way, we're doing derivatives and integrals. We start mixing them together a little bit occasionally here. So now I'm doing a derivative, please. This is e to the 2x times 2 from the chain rule. Okay, that ain't the answer.
Right.
Right. So, but now I proved to you that ain't the answer. What I need is something to cancel this damn 2.
Right.
What I need is
I have.
a half out here. If I had a half out here, that would work. But all right, hang on. Nah, this ain't the way. That ain't the way I normally teach it. Here's how I normally teach it. I'm telling you, we gotta try to fit this formula. So we gotta call the 2x a u. So we go over here and it's a process called U-substitution. We let u equal 2x. Now that would be easy, look. So then you can go up here and change this to e to the u. But if you change this to e to the u, then you can't have this be dx, which, I mean, now the variables are confused. Is it in u's or is it in x's? I can't have that. So if I change the variable to u's, I gotta change the dx to a du. But it's governed by this relationship. Listen, it's not just that dx is du. As a matter of fact, let's go over here. What is the du dx relationship? It's right here. You ready? You take a derivative. You take a derivative. Du is 2 dx. Oh, that's the relationship between du and dx. And I move the 2 over, divide by 2, and dx is 1/2 du. And that's what I use to replace everything here now. So here I go. Did I replace this correctly? Is that 2x my u? Okay. What about the dx? I need to replace it correctly. And this showed me how. The dx is 1/2 du. Now, if you don't mind, I like to pull the 1/2 out because it's a multiplied constant. So I pulled it out front. But that was me replacing the dx right there. You with that? Now, can you do the integral of e to the u? Yes. It's e to the u. I'm standing in front of it. Can you do the integral of e to the u? Yes, it's e to the u. And there happens to be a half out in front of it. So we're done now. Can we integrate it? Yes, it's e to the u plus c. There's a 1/2 in front. Don't leave your answer in u's. Go back to the original variable, which was x. So what is u? Let's take u back to, what was u? What was u?
2x.
2x. So here we go, back to the original variable. This is the answer. And that's the process, and I really want you to know the process, but there are ways to, I'm showing you the process. This is a real baby one, and in a day or two, you're good at this, and you probably can do this in your head. And one way to think about it is to think about it as a reverse chain rule. Listen, if you were doing a derivative, you would spit out a 2 from the chain rule. Well, you're doing an integral. So maybe you could say, since you're doing an integral, it spits out a 1/2, which it did. And you might say, well, why did it spit out a 1/2? Because it's the reverse of the chain rule. And maybe you could say that to yourself. I would rather you understood this. It spit out a 1/2 because of this process, this process. That's for real basic ones. I mean, right, here's another basic one. We learned this rule. The integral of cosine x is sine x. I would like to sort of generalize that rule to this rule. The integral of cosine u du is sine u. In other words, when it's just an x, this rule worked fine. When it's more than just an x, I kind of need this rule. I mean, this is what I use when x is more than just an x. When x is 3x or 5x squared or 10x cubed plus 17, or when x is more than just an x, we call it u. And this is our rule. So, watch out, hang on. Can we do the integral of cosine 8x? I can do all the steps. I mean, I really, I shouldn't do this. I should do all the steps, But if you followed these steps, then you know what's going to happen. The answer is going to be, when you integrate cosine, don't you get sine? Don't you get the sine of 8x plus c? But because of the 8x, it's going to spit out a 1/8. It sure will. And you can memorize it as a shortcut, but the truth is, I would like you to understand the process that leads you to that. Do these 3 steps here, and you'll see why that spits out a 1/8. Here, I'll help you. You let u equal the 8x. What's du? Du is, you're doing a little derivative right here. The derivative is 8 dx.
Yeah.
See, this is not magic. There's not magic going on. And now I replace everything in this integral. This whole integral gets replaced. It's a cosine of, what does that 8x get replaced with? U. What does the dx get replaced with? 1/8 du. Y'all see it? Y'all see it? I'll do it for you. Now you see it better now? Right. The dx gets replaced with 1/8 du. It's a multiplied 1/8. I like to pull it out front. And now this problem is the cosine of u du. How do you integrate the cosine of u? Sine u. Thank you. With a 1/8 out front. Done. So there are little baby ones like this. Little, I like these little baby ones. Look at this. I wonder if you can handle this. The secant squared of 5x. Do you know how to integrate secant squared? Shout out the answer. Tangent. She shouted out, the answer is tangent. The antiderivative of secant squared is tangent. How come I know that? The derivative of tangent is secant squared. The integral of secant squared is tangent. So the answer is tangent. So I'm done. The answer is tangent 5x. The answer is tangent 5x plus c, but I should have done a little U-substitution on that, and in my head I'm doing the little U-substitution, and the result is it spits out a 1/5. It does. And the steps that prove that to you are, you know, just like this, similar, just the same thing. Again, and yeah. So these are like little baby trivial U-substitutions, and then what I'm saying is at some point, maybe like I just did, you can quit doing the steps and just understand what you're doing and spit out the answer. Maybe. I'm worried about you though. I mean, I'd like you to really understand the steps. And the truth is, for more complicated U-substitution problems, you definitely need the steps. Let's do a more complicated U-substitution problem. I mean, this is a classic. This is a classic. The cube root of 5 minus x to the 4th times 7x cubed dx. I mean, look at this. This is a mess. I mean, this is a tough integral. In fact, there's just, can you come up with this antiderivative? Hell no. I mean, you gotta work hard to come up with this antiderivative. You gotta work on this. This is tough. I think you need U-substitution. But then when you do decide you need U-substitution, then you gotta decide what's U. And I don't know what you've learned so far, but U tends to be like inside a function. It's inside that E function. I erased all my good stuff, but the U was inside the cosine function. The U was inside the secant squared function. I think this time the U is inside the cube root. Right, inside the cube root. Good job. So the U is
5 minus x.
not the cube root, but what's inside the cube root. Right. All right, so now, once you declare something U, then the next step is find du. So how do you find du?
du equals -4x cubed dx.
Well, you take a derivative. I mean, I know you're in the middle of doing an integral, but when you're doing you take a derivative and you call it du. That's what you're doing here. Some people think I'm doing magic on the board here. I'm doing very logical steps, everything, and then I replace this. It's not magic when I replace this. All these cool notes replace this stuff. Well, then anyway, the derivative, please.
Negative 4x cubed dx.
Awesome,
Yeah.
awesome. All right, now, let's see what I do. Let's see, what do I do? I try to start replacing this stuff. You ready? And again, it's not magic. Now, this is a cube root of a bunch of crap, but what did I call that crap?
U.
U. Okay, so it's the cube root of U. All right, now, I'm going to write that as U to the 1/3, if you don't mind. It's cube root of U. All right, cool. All right, now, hang on. Let's see, what else do I need to do? That's 7. I don't see that 7. It's a multiplied 7. Can I just, I'm pulling it out here. I'm pulling the 7 out of my way. What'd you say? Okay, hang on. So I got the 7 out of the way. Now I see this x cubed times dx. You can handle this a few different ways, but over here I see an x cubed dx. I'm so happy. This makes me happy. It has to be like this, dude. If that was an x cubed and this was an x to the 5th, this probably be going nowhere. I'd be done. I'd be out the door, pissed off the rest of the weekend. Now, some problems, they can't be done. So when I set up these U-substitution problems, I'm setting them up so they're doable. So I set that x cubed out there on purpose so this would happen. This x cubed dx matches that x cubed dx. Now hang on, I want to replace that. If I want to replace that, I think I'll solve for this. So I think I'll divide by -4. Now, this is me doing it my way, but I like my way. You understand what I'm doing? I'm going to go replace that quantity called x cubed dx. I'm about to replace it with what?
Negative 1/4.
Right, and if you don't mind, I'll put the negative 1/4 out front. It's multiplied out front, and I'll put the du right there. That was me replacing that.
Yeah.
So it's not magic. You see all the replacement happening? It's all replacement. It's all substitution happening. You see it? Cool. So now you're left with this problem. Can anybody integrate a u to the 1/3? Yeah, it's a power rule. Yeah, you can do it. Add 1 to it, divide by, right?
Right.
Did you know way back at the beginning when you stared at that, did you know it was just going to be a nice power rule? You know, maybe not. It was totally disguised and horrible. But U-substitution makes it look good. It's just a little power rule. U-substitution has helped you simplify it into what it truly is. It's just a u to the 1/3. And the process of U-substitution helped you handle all these little details like spitting out the negative 1/4, blah, blah, blah. And anyway, here we go. This is a negative 7/4 out in front of, and now we integrate. U to the 4/3
3/4 will go.
times 3/4 plus c. So that's it. The problem's over. But you don't leave it like that. You put your x's back in. See, there was a lot of work to prepare the integral. Now when we did the integral, it wasn't too much work. It was just a quick power rule there. So now it's negative 21/16. The cube root, well, I'll just leave it like that. What is u? 5 minus x to the 4th to the 4/3 plus c. Looks wild. If I wanted to check it, I could do his derivative. It would be a power rule, be a chain rule, and anyway, if I did it and cleaned it all up, it would be that. But we just anti-derivative that and got this. This is good stuff up in 5.5. I mean, this makes anti-derivatives and integration a little bit more advanced. You couldn't integrate that much stuff until you learn this technique called U-substitution. With integration, we don't have product rules, quotient rules, or chain rules with integration. But we do have this powerful technique called U-substitution that kind of embroils all that, maybe, I don't know. Yes?
So how'd you get negative 1/4?
Well, so this is an equation, and there's a negative 4 on this side that's multiplied, so what did I do? I divided by -4. See, it's not magic. I mean, see, he's looking at this and he's thinking it's magic for a second. I mean, he's thinking, where the hell did that come from? Where did? But it all comes from something. You can. I took this derivative, -4x cubed dx, and then I wanted to solve for the x cubed dx. Why did I want to solve for the x cubed dx? Because I saw it up here in my problem. I saw an x cubed dx that I felt like I could replace. So what did I replace the x cubed dx with? Well, the 4 is in my way, so I move the 4 over. I divide by 4, -4. And I replace the x cubed dx with what it equals. It equals 1/4 du. So I replaced it with 1/4 du.
Okay.
Yeah.
And the power 4/3, right?
Well, that was me integrating. From this step to this step,
Okay.
I integrate. How do you know that? One way you know that is I do things properly. Sometimes students don't do things too properly. I do things properly. When I haven't integrated yet, I still got my integral symbol. And then when I integrate, that symbol's gone because I've done the integration. So from this step to this step, I did a power rule. I added 1 to the power. I added 1 to 1, I got 4/3. I divided by 4/3, which is multiplying by 3/4. So from here to here, I did a power rule. Any other good questions?
Well, yeah, I was concerned about that power 4/3. That was it, because when you integrated, I was thinking 4 minus 1 doesn't equal 1/3. 4/3 minus 1 doesn't equal 1/3.
I know, you were thinking that?
Yeah.
Are you still thinking that?
I don't want to think like that.
Right, it's wrong. Right, 4/3 minus 1 is 1/3.
Oh, I see what okay. Maybe I was thinking 4/3 minus 1/3. That's probably what I was thinking.
Okay.
All right. Other than that,
All right. Right. Yep. Errant thoughts. Yeah, it can get in your brain and get stuck in there like little bugs in a
Right.
computer. You gotta get rid of those little thoughts. All right. Cool. Any other good questions? I mean, that was a good one. It's a process, but it's set up for you. Again, one more time, I swear to God, if I changed the initial problem to an x squared, this problem wouldn't work. It just wouldn't work. And there's plenty of, I can make up terrible integrals that you just can't do. So I'm not going to do that. I'm trying to teach you how to do integrals you can do. But it wouldn't work. I needed that x cubed out there. So after doing these a little bit, what you start to realize is, what you start to see is, you know, if this is your u, you look ahead to the fact that, well, if this is your u, which is an x to the 4th kind of thing, well, then the du is going to be, if the u is an x to the 4th, the du is the derivative, will probably be an x cubed kind of thing. So you're kind of looking for that x cubed kind of thing to be part of your du, to take care of your du for you. I mean, you need that. And you look for it, you see it, and you realize this is going to work great. See, look at this. Look at this. The cosine of x cubed. Nobody can do this integral, but if I stick an x squared out on the end, now you can do this integral. What do? So this is my problem, and so I'm going to let u equal x cubed. What's du? 3x squared. I like to stop now and say, are you happy? And you're supposed to say, forget your personal life, just tell me, mathematically speaking, yes, you're happy. You got this x squared dx, you needed this x squared dx to help you finish this problem, because you replace all this stuff. See, the other thing that I haven't told you really is when this stuff gets replaced, this whole integral is in u's now. There should be no straggling x's hanging around. I mean, that would be bad. I mean, you can't be mixing the variables like that. The whole thing was in x's. It completely gets turned into a new variable, u. If the constants don't jive, we pull constants out front if we need to. But if there's like an extra x hanging around, that's bad. You can't have, that's bad. So this makes me happy. This is perfect. If I want to replace all this, here I go. This is cosine u. And what is all this? Can you tell me what that is?
1/3 du.
Good job. You see it, right. I mean, I usually like to move it over for you so you see it more clearly, but you were right. You move it over. 1/3 du is x squared dx. So that gets replaced with 1/3 du. The 1/3's a multiplied constant. I pull it out front, and now all I got to do is integrate cosine. How do you integrate cosine?
Sine.
Sine. So it's sine u plus c. But you don't leave your answer in u. You put your x in there. What was u? What was u?
X cubed.
X cubed. Thank you very much. I'm going to hit pause and take a little 2 minute